Hello, guys. Hope people are doing great. Today, we are going to see how to write a program that checks to check if the given number n is a prime number. Okay, so this is the problem that we are going to see today. But before actually getting into this problem, let's say we have to write another program. So, for example, write a program to check if n, a given number n, is an even number. Okay. Now, if you see, let's talk about the solution of this problem. Okay. Now, if you see from the description, the description of both the problems, then you will realize that from the description they look very much similar. Both of them are basically asking whether a certain property is true about a given number n or not. Like in the first question, it is asked like whether n satisfies the properties to be not to be a prime number. Whether in the second condition, a second program or second question, it is asked like whether n satisfies the conditions to call itself as an even number, right? The program description, at least, in some way they are the same. However, now let's see the solution of this problem. So let's see the like what are the things that we have to compute to determine whether the asked property is true about that given number or not. Okay, so in this case, what we have to do is we just have to do only one operation. That is, we have to compute the modulus of the given number with respect to 2. And if it turns out like n mod 2 equals 0, then that implies that the given number is an even number. Otherwise, if it is not equal to 0, so in that case, it implies that that given number is not an even number. It's very much straightforward. Now you should realize that no matter how small or big this number is, say for example n is equal to 31, in that case also you have to do, or basically, when I say you, it means like whoever is doing that computation, maybe a human being or maybe a computer. So in this case also, that computation model has to do only one operation, like say 31 mod 2. What is 31 mod 2? Now, since 31 mod 2 is equal to 1, it means it's not an even number, right? Or if the number is very big, say for example, n is equal to 312096421. So in this case also, we have to compute or only one operation, like what is the mod of this number with respect to 2, right? So based on that result, we'll be able to tell whether that given number is a prime is an even number or an odd number, like that. Now let's go back to this problem, our original problem. Okay, now in this problem what we have to do is we have to find out whether this given number n is a prime number. Now let's see by what is the definition of a prime number. The given number n is called a prime number if it has only two factors, 1 and the number itself, right? So for any number, if this condition is true, then we can say that it's a prime number. Now, say for example, now let's come to the question, like how can we say that the given number is a prime number? If that is the question, then what we basically have to compute is from 2 to n minus 1, whatever that n is, minus 1, up to within this range, we have to make sure that within this range there exists no such I such that n mod I equals 0. It means within this range there should not be any integer number that completely divides these n, right? If there exists a number here within this range that completely divides this given number n, we can say that for these n, at least this 1 along with this 1 and this I is also a factor. So in that case, certainly n cannot be a prime number. So this is what we have to do. Now if you compare the solution or the computation that we need to do while checking if the given number is an even number or if the given number is a prime number, you will see that when we're doing it for a prime number, it is not a single operation. Basically what we have to do is we have to check a given range of numbers, like we have to perform a certain number of steps actually based on the given number to find out if the given number is a prime number or not. So what we are doing here is repeatedly for each number within this range we have to check if n mod that number is equals to 0 or not, right? So you should realize that here this condition doesn't, this statement is not true. That is, here I said that no matter whether this n is small or big, you always have to compute only one operation. However, in this case it is not the case. Number of operations or number of steps that we want to compute or we have to compute actually depends on the given number n. Like if n is small, say for example n is equal to 31, in that case we want to or we have to or our computation engine a computing engine has to compute these range like from 2 to 30. Like it has to check within this range if there exists a number that divides this n completely. However, if n is big, say for example if I write n is equal to 3129604 or 1, so if I end this number with 4, then certainly it's an even number, so cannot be a prime number. However, if I end the number with this 1, now it's an odd number, and just by looking at this odd number it is not very easy to say whether it's a prime or it's not a prime. So basically we want our computing engine to compute within this range like 2 3 way up to 3129604, like whether there exists a number that completely divides this n completely divides this n, right? So so that is the computational model. Here we can say that the number of steps that we have to compute is actually proportional to the given number n. Whereas in this case, like when we are finding whether the given number is actually an even number or not, in this case the number of steps are always constant, right? It's only one. You can say like it's a constant step model. Whereas in this case it is not the number of steps that we want our computing engine or machine to compute is like proportional to the given number. So that is the underlying concept. Now more or less now we have an idea now what program or what are the instructions that we have to write in the form of a program that enables a computer to solve this problem, right? That is, we are now in like about to write the program for this given problem, like to check if the given number is a prime number or not. Okay, let's do that then. So how do we write that? Now see, what we have to do is our program has to go from 2 to n minus 1, right? And all these numbers are integer numbers. It means in each step we have to increase this number by 1. So how do we write the program? So for example, in our program, we want to store what is the number n for which we are actually checking the property. That is whether this n is prime or not. So that number could be anything, any number that we want to check. Just no. Since I'm hard coding the number, I can write here any number. Say for example 31. So if I want to check a different number, then I have to change the value of this number n. And then what we want is we want our program to iterate over this range. Like, in each iteration, we want to check whether that current value, say, yeah, we want to iterate over this range, right? So for that reason, what we want is we need a variable that actually allows us to iterate over this range. So, and that iteration starts at 2. So I'll be writing, okay, say the variable is 2i, and then it starts at 2. Then comes the loop, like that allows us to do the actual iteration. Say while the value of I, as long as the value of I is less than or equal to n minus 1, that n you have to write in capital, because say n minus 1. Now see here I have written less than or equal to n minus 1. See, we want these iteration to happen from 2 to exactly n minus 1, right? So that is why this I is less than equal to n minus 1, as long as this condition is true. Another way of writing this condition could be like whether I is less than n or not. So in that case, both these two conditions actually means the same thing. Okay, you should realize that point. Like it's not just, it is not the only one way of writing the condition. You can write this condition in any way, as long as it fits your need. So while I is less than equal to n minus 1, as long as this condition is true, what we want to do is we want to check if that given number I, if that given number n mod I equals 0. It means if the current value of I completely divides the given number n. So if it is the case, then we immediately know that the number is not a prime number. So I can write like not a prime. And see here, like within this range, when we are doing the searching, like say for example, initially I is 2, then it goes to 3, and then 4, like that, then 5, like that. At some point of time, suppose this particular number, suppose at some point of time I is pointing, or I is having this particular value, and that value completely divides this given number n. So immediately, as soon as we find that particular number, or find a number, or find the first number that completely divides this given number n, we know that the number cannot be a prime number. It means what? There is no point of continuing the search, this part of the search, right? So what we can do is, as soon as we find the match, then we can break the loop. That is, we can terminate the loop. That is, we can write here a break statement. So it means what? As soon as we find a match, we know that the number cannot be a prime number, so that like immediately we can print the result and we can break. Break means what? It will take the control out of the loop. Now we should realize at this point, or you should know at this point, that if is not a loop, while is the loop here. Okay, so this break will take the control out of this while loop. Now if it is not clear right now, what does it mean by now when I say like it takes the control out, so you'll come to know it in a moment. Okay, just hold on. Now if it is not the case, now you see, again I want you people to realize something here very properly, that see, if this condition is true for the first time, say for any value of I within this given range 2 to n minus 1, suppose there exists an I that satisfies this condition, that first I, the first time this condition becomes true, then that time itself it will print that it is not a prime, and this break will be executed. It means what? Whenever this condition becomes true, immediately after that this break will be executed and the loop will be terminated, right? Now if this condition is not true, then this part of the code will never be executed. So as a result, uh, it will pass the control to the next point here. Now my point is, what I actually wanted to tell you is that, should we write here an else, and then we write like, see, if this condition is true, then we want to do this. Otherwise, what we want to do is, we want to increase the value of I by 1, because we want to move to the next number, so we can write it in this way. So this is fine. I mean, you can write the program in this way. However, at the same time, I want the people to realize that if I do not write these else also, like even if I do not write that else, and then simply I write I is equal to I plus 1, then also the program is going to work. Right? Why is it so? Because the clue is like, if this condition is true, anyhow this break will be executed, and the control will never reach this point. If this condition is true, this I equals I plus 1 will never be executed. However, if this condition is false, in the else part, if you do not write, suppose you write the code in this way, then it means that if this condition is false, nothing is to be done. Since we do not write, suppose, this else part, it means in the else part we do not have to do anything. And then the next statement is your I equals I plus 1. Anyhow, this I equal to I plus 1 will be executed. Whether you write here an else or you do not write here an else, both the ways the program will work actually. So you just pause the video here for a moment and you make it clear in your mind. Okay, well, whatever am I saying is actually makes sense. Okay, so it is up to you. You can write this in this way, like else I equals I plus 1, or directly I equals I plus 1. Okay, and after that, this is the end of our loop. Actually, see here, once this is the end of our loop, like this is the body of the loop. Like once this body is over, then we know that the control will immediately go back to the condition part. Like it will go back here and will again check the condition. Now you see, in each iteration, we are increasing the value of I by 1. And suppose this condition is never true within the given range, then what will happen is at some point of time, this condition will become false, because you see, we are starting at 2, and in each iteration, we are increasing the value of I by 1. So at some point of time, it will become 3, 4, 5, 6, 7, and like that, at some point of time, it will become equal to n minus 1. When this I equals n minus 1, this condition will still be true, and as a result it will check if this is true or not. Suppose this is not true, then again it will increase the value of I by 1, and then again it will go back to this point. So it means what, when I is n minus 1, then it gets inside the loop, and then it increases the value of I by 1. The value of I will become n. Now, when the value of I is n, and then when the control reaches this point to check the condition once again, so at some point of time, this condition will become false, and then the control will go out of the loop. Right now, see here, the control will go out of the loop. It means the control will reach this point. Let me use the eraser for. Okay. Okay, anyhow, the control will actually reach this point, right? That is, if this condition is false, then that this is one way of, one way through which the control can reach this point. Now, so now let's suppose this is our program, like from this point, n equal to 31, I equal to 2, while I is less than equal to n minus 1, and this is the program that I wrote. Say, let's see what will happen if I execute this program, or let's see whether is it the complete program or not. Okay, let's trace the program. Suppose if I give n is equal to 31, then in that case, what our program will do is from 2 to 30, it will check if there exists a number that divides this n completely, right? So for 31, what will happen is, no matter what the value of I is within this range, see here, I'll start from 2 and it will go way up to 30. And for all these values of I, like 2, 3, 4, 5, 6, 29, and 30, this condition will be evaluated as a false condition, right? So that time what will happen is, if the given number is 31, then this condition will never be true, right? As a result, every time the control gets inside the loop, this I equals I plus 1 will be executed. So at some point of time, I will reach this 30, this number 30 here, right? And that time it will, when it goes out of the loop, like when I is 30, it comes inside, this is a false statement, this will execute this I equals I plus 1. So that time the value of I will become 31. So when it becomes 31, the control will go out, because 31 is less than equal to 30. That will be false condition. So it will take the control out of the program. So as a result, and suppose this is the end of the program. Suppose I didn't write. See, when the control goes out of the while loop, now here I have not written anything. So as a result, it will consider, okay, that is the end of the program. And as a result, on my output screen, suppose this is my output screen, there I am not going to get any, any output, a blank screen. But what exactly is, the output that we were expecting when we gave the number n equal to 31? We were expecting that the program prints us here like n is not a prime, right? It's not a prime. So that was the output that we were expecting actually. Now, how do we know that? Where can we actually print that n is not a prime? Now, see, can we print here? Like you might be thinking, can we write here an else and then write print not a prime, print a prime? So here, sorry, we were actually expecting that n is a prime. Actually, here for n equal to 31, we are expecting that n is a prime, right? So and in this case it is not giving us the output. Like if I give n equal to 31, it is not giving us the output, right? Say now let's try with a different number. Say for example n equal to 30. Then what will happen is our program will check from 2 to 29 all these numbers, and we know that within this range there exists at least one number for some value of I. Like say when the value of I is 2 itself, right? So that time this condition will become a true condition, like 30, sorry, 30, yeah, right, 30 mod 2 equals 0. So immediately this condition is true. It means like it will print it's not a prime, not a prime on the screen, and then it will execute this break. So when it executes that break statement, it will take the control out of the program, right? And that since after that nothing is there, nothing will happen. So as a result, on my output screen, I'll see this line as an output. So we realize that when we give a prime number, our program, actually this program doesn't give us an output, like it doesn't print anything. And when we give a non-prime number, it gives us the output, right output, like it says that the number is not a prime. So what modification do we have to do here to make that correction? Like whenever we give a prime number, we want our program to actually print that it is a prime number. Now see, if it is not a prime, anyhow our program is working fine. I mean, at some point of time this condition becomes true and it prints when that the given number is prime, and then it's execute breaks and then it reaches here, done. Now, to know, like, or to print like given number is not a prime or given number is a prime number, what we have to do is whatever we have to do, we have to do it here at this point. Now, see here, if you think for a moment, then you know that this point, this particular point actually of control can be reached in two different ways. One way is this one, another way is this one. That is sometimes due to the execution of this break statement, and sometimes due to the failure of this condition. Two different parts, right? Now, if I ask you, is there a way that we can distinguish, or when we reach here we can actually determine based on some logical things, like which path did we take to reach this point? My question is that when you reach here, if logically can you determine whether your program took this path or your program took this path, right? So if you think, you should realize that yeah, there is a way actually. And what is that way? If you compare, the value of I here, like at this point, if you check if the value of I is equals n, see here, you should realize that if the control goes out of the while loop, or if the control reaches this point due to the like via this particular part, it means that it was due to the execution of break. It means the control was somewhere inside the while loop. It means at that point of time the value of I must be less than n, or less than or equal to n minus 1, right? Then only this break can be executed. Like whenever this, like if the control reaches this point due to the execution of this break, it means the control was there inside the while loop, or inside the body of the while loop. It means the while condition was true at that point of time. It means the value of I must be less than or equal to n minus 1. However, if the control reaches this point using this path, then the condition, so it must be using this path in the sense like due to the failure of this condition, we should realize that the value of I must be equal to n. See, for different values of I, like any value which is not greater than or equal to n will satisfy this condition. However, since we have started from 2 and we are moving in this direction one at a time, so n will be the first number. N will be the first number that will actually violate this condition. So if this condition is false for the first time, that time itself the control will go out of the loop. So as a result, here we can conclude that, like, if we check this condition, whether the value of I is equals n or not. Now, if this condition is true, it means we are sure that the control reached this point due to the failure of this condition, right? So if it is the case, it means like if the control reaches this point due to the failure of this condition, it means that our program actually checked all these numbers starting from 2 to way up to n minus 1, and it didn't find a match. That is, for all these numbers from 2 to n minus 1, this condition was false. It means there exists no such number I that come within this range that completely divides this n. It means n is a prime number. So we can safely write here that print given number is a prime number. Now that completes our program actually. Now let's write the code in Google Colab and do some experiment there. Okay. here. So we'll directly write the program. Say, for example, we have a variable n where we want to store the number that we want to, verify whether that number is prime or not. And then we need that variable that will allow us to iterate over all the numbers from 2 to n minus 1. So that, let's call that variable I, and say I that starts from 2, I equals 2. And then the main loop now, while as long as the value of I is less than or equal to n minus 1. So if I write equal to, then I have to write n minus 1. If I write less than, then I have to write n. And I want the people to, pause for a moment. If this thing is not clear, think for a moment, like whatever am I saying is true actually. So I is less than, or I will go with this less than or equal to n minus 1. And as long as this is a true condition, so I want the control to come inside the loop. And then I want, as soon as it gets inside the loop, I want to check this condition. I want my computer to actually do this thing. I want my computer to check this thing now. Like if the given number n mod I equals 0. And if the computer finds this thing, this condition or this expression, to be true, then what I want my computer to do is immediately, uh, you know, um, to come to an immediate conclusion that the given number n is not a prime number. And if it is not the case, now, as I said, no, I can go with this else part. Else, just increase the value of I by 1. Write it in this way, or what I can do is I can completely omit this else part. That is, else I do not want to do anything. I do not want to do anything. However, irrespective of that condition, like independent from that if condition, I can write a statement here: I equals I plus 1. However, what I want to do at the same time is that if it is not a prime, if I know the result, immediately spitting out the result, immediately after, printing the result on the screen, I want my loop to terminate. Like, because there is no point of now continuing the loop. There is no point of searching, after once we get what we were searching for actually. So if n mod I equals 0, then it's we know, like we know for sure that the given number is not a prime number, and also there's no point of continuing the loop up to n minus 1. So we can simply execute this break and we can terminate the loop. However, if the condition is like after that, we are writing here, irrespective of this condition to be true or false, we can write here I equals I plus 1. Now, here again, I want to, like, one more time, I want to tell you that when I say irrespective of that condition to be true or false, but you should realize that if this condition is true, then this line will never be executed, because if this condition is true, then this break will be executed and it will take the control out of the loop. As a result, this line will never be executed by the computer. Anyhow, that is the end of the loop. And then after that, once we are outside the loop, there one thing is still left. Like, we have to know, like, how the control actually reached this point. Which path did our program take to reach this point? And how do we do that? We can ask the computer. Now we check if the given value of I is equals to the number n. That is, whether we took this path, or whether our program took this path or this path, right? Now, if this condition is true, then we know that the path which was taken must be this path, that is due to the failure of this condition. And we know that if the control goes out of the loop due to the failure of this condition, logically we can conclude that this number, that given number n, is not n is a prime number, and that is the end of our program. Now let's first run this program and check if it gives us the right output. Then we'll play around with this. With this program. Let's execute the program and say it says it's a prime number. Okay, for this number n31, it's okay. This is the right answer. So for example, now if I give a number n equals 30, it's not a prime number. Okay, it gives us the output, right? Now let's try with some number, like say 55. Okay, so it's not a prime number, so it will say that it is not a prime number. Okay, and say give a number, say for example 93. Let's see whether it's prime or not. Is not a prime. 91, not a prime. 97, right? Okay. Now, done. The program is written and all, right? Now let's go back to our theory part here and realize something more about this program. Now, see, when I said, like I said, you people, that let me change the color just for a change. Let me pick this color. Now, I told you people that this program, like when we are checking that given number is prime or not, that program actually depends on the given number. That the number of steps that we want to execute is proportional to the given number n. What I mean by that actually, say for example, we give eh, say okay, let's see what we do actually. Okay, like what we are doing when we're checking that the given number is prime or not. So we are actually searching within this range, like 2, then 3, then 4, way up to n minus 1. We are searching within this range and see, you make it sure in your mind that if the number is not, if the number is a prime number, then for all these numbers, we our program has to go through all these numbers. If our number n is a prime number, then our program has to go through all these numbers. Then only, that is, our program has to reach this point. Only then our program can say that the number is a prime number. However, if the given number n is not a prime number, then our program will find a number I somewhere within this range. It means what? Our program will terminate abruptly somewhere here within this range, anywhere. It could be here, it could be here, it could be here, or it could be anywhere. But it doesn't have to go through all these numbers, certainly. That is for sure. Right? And you should realize that fact now. Now we can say that, like, if the number is prime, in that case our program has to do the maximum work, right? I mean, if the number is prime, then our program has to do the maximum work. And if the number is not prime, then always our program has to do, some fraction less, actually, like, based on the, location of the first factor. However, always we can say that our program has to do less work if the number is not a prime number. If the number is a prime number, our program has to do more work. And see, again, we know that the number of steps, or the number of work that our program has to do, because of the nature of the problem, is actually proportional to the given number. Because this range will, become larger if n is large, and this range will become smaller if n is small. That is quite obvious, right? It means what? Suppose now if we give a big number, suppose if I give a number like 12960429662, if I give a big number, and if that number is a prime number, then certainly we cannot say that it will go up to, this point. I mean, the worst case will not happen, right? The program will not do, has the program will not have to do as much work here, because clearly it's a even number. And see, in the first step itself, the program will know, that is, as soon as it computes like that given number n mod 2 equals 0 or not, so it will come to know, okay, it equals 0 and it is not a prime number. But if I give it a very large prime number, then what will happen is the program has to go through all these steps, and it will take the program more and more time, as I increase, as I, make this number bigger and bigger. Okay, whatever I'm saying, if no, it should, if it is not very clear, now let's see this example, and that will make some sense. Okay. To do that, what we will do is we'll play around with this program. Now let's for that, I had this prime number list. This is a website like primes.utm.edu, and it's a I mean, it's a website. You can get the data from there for free. Anyhow, this is a prime number. Say for example, this number, all these tick numbers are prime numbers. Say for example, I give my computer to check whether this number is a prime number or not. It is a 7-digit prime number, so I'm giving it to my program. Say this number here. I want my program to check whether this number is a prime number or not. See, completed at, okay, it's a prime number, so 0 second. It is not taking much time, actually. The time taken is immediate, actually. You can see that immediately I click on this play button, almost immediately we are getting the answer. It's a prime number. Now let's say I change my digits from 7-digit number to 8-digit number, and these are some 8-digit prime numbers there. So what I do is I copy any one of them, Control C, and then I check. I ask my program to check if this is a prime number or not. Executing, it is saying 1 second, 2 second, then 3, 4, 5, 6, 7. I'm just giving a rough estimation. 8, 9, 10, 11, 12, 13, 14, 15. So it's saying in no, it took almost 15 seconds. So when the number was like, see what I'm doing here is what I'm trying to do here is I initially gave a 7-digit number. So that number actually immediately, say 1 second it took to compute our program to compute that it is it's not a, it's a prime number for 7 digit. Now when I gave the program an 8 digit number, it took around say almost 15 seconds, right? That is when I increased my the magnitude of the number by 10 times. 7 digit and 8 digit, 8 digits number are at least 10 times bigger than 7 digits number. So that way it took like almost 10 times more time, 1 second and approximately 10 seconds, right? Let's play around with, like, let's see whether it is true again or not. Okay, like I give another 10-digit number or 7-digit number there, 7-digit number there, like anyone. This is a 7-digit number, 3, 4, 5. Oh, it's an 8-digit number, 1, 2, 3, 4, 5, 6, 7, 8. This is an 8-digit number. Okay, 8-digit number is taking actually 7 seconds or 10 seconds approximately. Let's give it another 8-digit number, like say this one. This one. And yes, see how much time it takes. 1 second, 2 second, and you can count by yourself. It will take more or less same amount of time. Like it's a prime number. It gave me the result in very less time. It's a prime number in say approximately 3 or 4 seconds. How many digits? 3 digits and 6 digits, 8 digits. Okay, let's try with another 8-digit number. But again, no matter, oh, okay, let's see how much time does it take now. 3, 4, 5, around 5 seconds. So we can overwrite our previous assumption that it was taking 10 seconds. But anyhow, it is taking more than 1 second. That is that that thing some that you should realize, right? Now say I give another 10 digit, another 7, 8-digit number, like 1, 2, 3, 4, 5, 6, 7, 8. This is another 8-digit prime number I'm giving, and we can expect that more or less it will take 5 seconds or 4 seconds, like that. So 3 or 4 or 5 seconds, right? Like that much of time. Now, suppose we increase the number, magnitude of the number by 10 times. Instead of giving a 7-digit number, let's give it an 8-digit number. So 1, 2, 3, 4, 5, 6, 7, 8. This is a 9-digit number. 1, 2, 3, 4, 5, 6, 7, 8. This is an 8-digit number. Let's give this number and check. We are increasing the magnitude 10 times, and see this will more or less take more time than compared to the first one. 5 seconds, 6 seconds, 7, 8, 9, 10, 11, 12, 13 seconds approximately. Okay, when I give a 3, 6, 8-digit number, it is taking me around 30 seconds. Let's play with some last 8-digit number, say 1, 2, 3, 4, 5, 6, 7, 8. This 8-digit number, I check. Now I give it. So you just count mentally how much time. More or less, it will take some 12, 13, 14 seconds, right? Say 4 seconds, 5 seconds, 6 seconds, 9 seconds, say 10, 11, 12, 13, 14, around say 14 seconds or something. Okay, more or less. It is like, you should realize that 7 digits number, 8-digit numbers are taking more time than 7 digits number, right? Almost more than twice, right? Now see, if I give it as a 9-digit number, like say 1, 2, 3, 4, 5, 6, 7, 8, 9, 9-digit number, if I give it a 9-digit number, then the program will take more time now. Let's say this is a 9-digit number, 369, and see, it will take much more time than a 8-digit number. So 12 seconds, 13 seconds, 14 seconds, 15 seconds, 16 seconds, 17 seconds, 18 seconds, 19 seconds. I have no idea when it will stop, but we'll try to get some idea actually. 14 seconds. 33. Wow, it has taken a lots of time. 33, 36, 37, 38, 39, 40, 42, 45, 50. Mm, how much time? Say it was 4 times bigger, then 4 times bigger. 18 into 4, 80 seconds approximately. 70, 60, 70, 80 within this range it'll come. Because when it was a 7-digit number, it took us like approximately 4 seconds. Then for 8-digit numbers, took us approximately, um, you know, mm, 16 seconds or something. And for this one, it is taking us a last 80 seconds, more than 80 seconds. So it's like 86 seconds, 87 seconds, like that. But anyhow, certainly do not worry. This process will stop at some point of time. It's just a matter of time. But now it should give you the idea. Now, see, the computer is not always like, it cannot do things always. Like when I check this program with a very small number, it gives us the result immediately. That should not give us the idea that it will give us the output immediately for all the given inputs, right? As your size of the number becomes bigger, your program will tend to take more time. Your computer will tend to take more time. So according to this Google Colab, it took like 2 minutes, like approximately 120 seconds to compute, or like to compute whether this number is a prime number or not. So this number was a prime number, and that is why it gave us the right output. But thing is that it took a lots of time. See, now you should realize, like, see, when I give it as a 7-digit number, you should realize now, see what is happening here. A rough estimation, okay? When I gave it as a 7-digit number, it took approximately, say, these are my numbers here. Like, I give it as a 7-digit number, it took approximately 1 second. I give it a 8-digit number, it took approximately, say, you know, how much time did it take? Like 4 or 5 seconds. And I gave it like, say, a 9-digit number, it took us like 120 seconds. Like somehow it is going, increasing in this way. But anyhow, we can plot that thing. I'll tell you how we can actually, I'm just giving you an idea, not the exact thing. We can actually plot such a graph, and we can evaluate, like, how, based on our input, the program, the time taken by the program is changing. And that is quite an interesting area of, like, area to study actually. But anyhow, will not move into that direction much for the time being. Just I want you people to realize that, uh, your program, whatever the program you are writing is, you should not have that idea that since you are using a computer, it will always give you the output immediately. It's not that. Actually, it depends on the underlying computation model, like what you are actually computing, in what way you are computing, or in what way you are asking the computer to compute the thing. It depends on that thing. And theoretically, we can always get some idea about how much time this computer will take, to solve a particular problem. And also, if you extend this idea, you should realize that, there might be some problems for the computer also, which is very difficult for the computer also to compute in a very short amount of time. Okay, that you should, put in your mind. You will encounter that thing whenever you're doing research or anything. You will encounter such problems. There are some problems which cannot be solved by the computer also efficiently. I do not say that it cannot be solved by the computer. I say that it cannot be solved in an efficient way. Okay. So that idea you should get from this program actually. Now if you suppose there is no limit actually of on the number of digits that a prime number can have. So basically here I can write any arbitrary large number, and I can ask my computer to check if that number is a prime number or not. Now you should know that if I give here a 10 digit, 12 digit, 13 digit, 14 digit number, it will take even hours for this program to execute and to verify just a single number whether that number is a prime number or not. Okay, now that's all for the time being. Now but before leaving actually, I want to tell you here one point that okay, although just a second, something is happening outside, just 1 minute, let it pass by. Okay, so I want the people to hear. Here I said that you know this thing, like our input, that number, our number of steps that our program has to execute is proportional to given number n. When I say disproportional, it means like we know, like proportional means some constant number of n, right? Now this constant number could be one, or this could be a fraction also, say point 0.2, or this could be a fraction like 0.001. Now we'll see here in this program, whatever the programs that we have written here in this program, this proportional constant is almost one, because you know in the worst case we are actually checking all the numbers, we are actually checking all these numbers from 2 to n minus 1, right? Our program is going through all these numbers, but we should realize that we do not have to, like logically if we think for a moment, we'll find a better cutoff. Like instead of going all the way up to n minus 1, we should be able to find some cutoff here, like some number here, some very specific number here that makes that allows us to say that okay, if we have checked up to this point and if we didn't get any maths up to this point, then there certainly cannot be any solution within this range. So if we can actually logically come up with an idea that gives us such guarantee that okay, there exists such a number, that up to that number, if we have checked, if our program has checked and didn't get any maths, then for the rest of the things it is sure that there cannot be a solution. So in that case, if such type of logical conclusion if we can derive somehow, then we can make our program more efficient by reducing this constant actually. Okay, instead of one, now it could be only a fraction of that thing. So that time also our program will be proportional to the given number n. However, if that constant is small, you can say that like if our program by default takes say 10 seconds to execute for a certain digits number, then if with a smaller constant you can expect it to execute in 1 second or something like that. Okay, that is what we can actually improve our logic. There are still scopes here in this program that we can improve our logic here, and we can improve the the execution time or of this program. Or what we can do is, in other words, we can actually reduce the number of steps to be executed by the computer to come to a conclusion when that given number is a prime number. We'll see that thing in the next video. But if you have the answer, if you already know the answer, or if you want to find out like uh, yeah, and or if you found that answer by yourself just by putting some pressure in your mind, then just let me know in the comment section. Okay, we'll discuss about that solution in the next class. Have a nice day.